So moving on from the previous video, you can see I've actually filled in all of the quantum numbers for this next set of energy levels. I probably haven't drawn this perfectly to scale, because we'd have to squeeze in a few more here. But you know what, to satisfy the entire periodic table, you only need about not even 60 of these levels, and that covers the entire periodic table. That's all of the energy levels that you need to get up to element 118. And in first year chemistry, most of the time, we're not even going up that high in the periodic table. Each of these energy levels can hold up to 2 electrons. It can hold no electrons, 1 electron or 2 electrons. If you had an atom which only had 1 electron, for example hydrogen, in its normal state, what we call the ground state, that electron would be down here at the bottom. Why? Well, the electron likes being as low as it can possibly go. That gets it nice and close to the proton. It likes being close to the proton. If I had helium, which has 2 electrons, they'd both be down here in this bottom level. But when I get to lithium, which has 3 electrons, it can only fit 2 electrons down here, so the third one needs to be up here in 200. And you can see it just continues like that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then they're all full. 13, 14, and I skipped 11 and 12. Yeah. Anyway, you get the picture. It's called the Aufbau principle. It's filling up these energy levels from the bottom up as you go through the periodic table. Now, what do these numbers mean? Do they have any sort of physical meaning? Yeah, they do. So the energy level sort of has a shape associated with it. The shape represents kind of where the electron is found with respect to the nucleus. Does it spend most of its time close to the nucleus, is a little bit further away, and so on. And the general rule is the 2 electrons here, they're really close to the nucleus. And as you get further and further up, on average, they're further and further away from the nucleus. Electrons are moving around all over the place inside the atom. So an electron up here in this energy level can, every now and then, be closer to the nucleus than an electron down here. But on average, the electron up here in this higher energy level will be further away from the nucleus. So the size really corresponds to the first number, 1, 2, 3, and so on. It only goes up to about 7, and then we're done. These shapes that I was talking about, there's only a few that you really need to remember. Some of these energy levels have like a spherical shape. Some of these energy levels have what we call a dumbbell shape. It's like an infinity sign. And some of these energy levels, the ones with the second digit as a 2, they have like 2 infinity shapes crossed over. It's called a d-atomic orbital. So if you like, the first number corresponds to size, or energy, as we like to say. The second number corresponds to the shape of the orbital. And the third number corresponds to, well, which way is it pointing? If you're thinking in 3 dimensions, think of something on an x, y, z axis. These different shapes might be pointing in different directions. So those p-atomic orbitals, they could be the infinity sign ones. They could be pointing along the x-axis, the y-axis, or the z-axis. So this third number corresponds to orientation. So the first number, orbital energy or size. The second number, the shape. And the third number, the direction that that shape is pointing in. So that's what these quantum numbers mean. Now you'll notice from your notes that we have a table of rules for what sort of quantum numbers you can have. So see if you can learn those rules, and by following those rules you'll realize you can only have a finite set of energy levels. There's only a certain limited number that are actually possible.